So this is a variation of a very classical problem. When I remember when I was very young, people asked me as a math puzzle for any pentagon like this, what's the sum of the interior angles, right? So the problem is to actually what? Doing a lot of what? Symmetry. You can say this is X, Y, Z, W, what's the letter? We like U, or maybe just A, B, C, D, E, F, right? Right? And then the relation between them and the what? The interior angles, right? And then for this one, you also have a very nice but slick way is what? You realize that this angle is actually, if this is A, B, C, D, E, this angle is the exterior angle, right, of this triangle. So this angle is actually C plus E. And likewise, this angle should be what? B plus D. So now you bring all these 5 angles into one, so of course that's 180, right? I remember that one took me a week, or maybe more, to really see this, right? So this is a variation of this. So we have all these letters here. I think that this time it might not be easy to see this one. So actually going more systematically might be helpful. For example, this A1 is grouped with these 2 angles. Say this is X1, Y1, right? And this is what? Also Y1, right? So this is, I would just say this is X2. Make it even more symmetric. X2, Y2, X3, Y3, and then so on. So what we know is A1 plus X1, Y1 is 180, right? Or this problem is better to see them in a symmetric way, right? And then similarly, we have all these equations all the way to A5, A7, X7, Y7, equals this. So if we add them up, this is something we want to know, the sum. And here we have these 2 groups. And we have 7 times 180, right? So how do we see how to add x1 through x7? x1 is here, x2 is here, x3 is here, x4 is here, x5, x6, and x7. They basically what?
Those basically 7 exterior angles, and they should of
the inside heptagon, right?
Okay.
So they should add to 360.
So they should add up to 360.
And those are also,
that's another set of what? Heptagons, exterior angles. They are basically the same, right? This is another 360. So we know S is equal to 2, 2, so they have 360, 180, so 540, right? And over here, I think our audience can do similar things about here also, right? So that's kind of like finish our proof. But why there's no general results like this? Because, for example, almost all the students know the interior angles of what? Of a hexagon, right? Or the interior angle sums of what? Hexagons, or the inside of the polygon, right? Well, we can make stars. It seems like we can make theorems like this also. Seems like they follow a very nice pattern, right?
well, our proof I think is not going to work when we have a bigger polygon.
Why is that?
Because here for the pentagon we assume that something inside is a pentagon. There for a heptagon we rely on the fact that when we draw the star, inside we get a heptagon.
Yes.
And maybe it's there too.
Maybe it's even here, right? But actually, if there are more sides, we are not guaranteed if you build a star like this, the interior is actually what? A hexagon anymore, a heptagon anymore. So that thing completely could what? Basically change, right? So maybe we will talk about it next time. Find an example. For example, it's a 9-sided polygon. And if you draw stars like inside, you might not get a what?
An interior
Interior star. Okay?
It will get messy.